Okay, we want to do a little bit with logarithms. Get a bit of an introduction to the logarithms and some of the rules that you use to manipulate logarithms. So we start with the basic exponential function and the log base 2 function, which are basic functions that we learned about and became very familiar with early in the course, hopefully. Okay, so here's our table for the basic exponential function. We get the basic logarithmic function by swapping the two columns. Okay, and that's going to be our inverse function. So y equals log 2 of x is inverse to the 2 to the x function, and it follows that c equals 2 to the a, which is an instance of y equals 2 to the x. Well, if y is c and a is x, then over here x is going to be c and y is going to be a, and this expression will give us this, that a equals log base 2 of c. So if c equals 2 to the a, then a equals log base 2 of c. These two are equivalent. And of course that says that if this is so, then, well, we identify a, b, and c here, and we come back over here and see that if this is true, this must be true. Another way of saying it, which should be intuitive if you've done what we've asked with the tables, is that if you have a table for x versus y equals 2 to the x, and you have a here and c here, that matches x equals a and y equals c. Okay, so 2 to the x would be 2 to the a, c would be your y value. Then when you invert the function, you got to put c here and a here, so c is now x and a is now y, and you get this. Now you want to think through that. You really kind of want to absorb that, at least. I think it's a really good idea if you do. Okay, so now we have the equation 2 to the x minus 1 equals 7. Let's just see what good the logarithm could be for that. Now the key is you have logarithm buttons on your calculator, so you can calculate logarithms. And I'm going to show you exactly how that's done in a minute, because you don't have the button you need to most easily calculate this. Some calculators maybe do, but most don't. Now we'll work it out. You'll see how this works. Okay. Okay, so you have 2 to the x minus 1 equals 7. Well, that is of the form 2 to the a equals c, this form here, with a equal x minus 1, because a is the exponent, and c equal 7, because, of course, c is what 2 to the a equals. Okay, well, there's a and there's c, so that's equivalent to this, where a goes here and c goes here. The form a equals log base 2 of c. So if a is x minus 1 and c is 7, you get x minus 1 equals log base 2 of 7. Well, that's an equation that's very easy to solve. We just add 1 to both sides. We get x equals log base 2 of 7 plus 1. And then you can evaluate log base 2 of 7. I can evaluate it by interpolation. I can evaluate it by drawing a graph, but those are approximate evaluations. So is the calculator's evaluation. It's going to be approximate, but it's going to be much more accurate, many more significant figures. Now I estimated it by simply sketching this curve that I know has pretty much the shape of a logarithmic curve, because I've drawn a lot of them. I thought I'd drawn it probably about right. Then I put, the x and y axis on it. I think I had the x and y axis before I drew the curve. And then I labeled it. Okay, I said, okay, well, let's just say if this has got to be 1, this is where x equals 1, so x equals 2 has to be here, x equals 4 has to be here, and x equals 7 is a little short of x equals 8, which would be twice as far from the origin as x equals 4. So I said x equals 7 is about here, and then I drew this projection line. Okay, it's not particularly accurate, it's not particularly horizontal. Of course, neither is my x-axis. Okay. Then I went ahead and did the projections for 2 and 4. Of course, log base 2 of 2 is 1. Log base 2 of 4 is 2, as we know from the table, if not from just experience. And then, if this is 1 and this is 2, this is a little short of 3, so I said maybe that's about 2.8. Okay. So now I plugged in 2.8 for log base 2 of 7, added 1, and got 3.8. And I think if you put this into your calculator, 2 to the 3.8 minus 1 is 2 to the 2.8. You've got to get something reasonably close to 7. It's not going to be within hundredths, probably not even within tenths, but it won't be too many tenths off, I don't think. Okay. And if it is, I've got an excuse because it's hard to do these, to estimate them. But I don't think it's going to be that far off. Okay. Now, you can actually calculate with your calculator. That's very easy. You have a log button on your calculator. You also have a natural log button, ln. Okay, an log and an ln. And you might even have a log base 2. If you have a log base 2, you don't need to do this. You can just do this. But I'm showing you this because it works for any other base as well. So log base 2 of 7 is log of 7 divided by log of 2. You find the log key in your calculator, you can enter this and press, press calculate or whatever, and you're going to get a number that's probably pretty close to 2.8. I mean, it won't be off by more than a tenth. I'm as sure of that as I can be. Okay. You could also do that using the natural log button. Natural log of 7 over natural log of 2. Doesn't matter which log you use, it's always going to give you the same result, as long as you don't mix up and use a natural log for the numerator and log log for the denominator, or vice versa. If you mix your log functions up, you're going to get something that is going to require some serious correction. Okay, so right away we see that we can solve this equation. Now, if you try to solve this equation using standard algebra techniques, there's nothing you can add to both sides. There's nothing you can divide both sides by. There's nothing you can do, no root you can take, nothing you can do to get a hold of that x until you use this, okay? Until you use the equivalence between logs and exponentials. And what you've done is you've taken an equation, an exponential, that's an exponential in x, and changed it to a logarithmic equation where x is no longer in the exponent. And you can handle it, you can deal with it. Okay? Now we solve now 9 to the 2x plus 4 equals 437. Perfectly good number. One of my favorite numbers. What if that thing is prime? Not divisible by 3, it's not divisible by 7, so chances are pretty good, certainly not by 11, and 13, 30, 390, 47, no, not by 13, so it's starting to look like that might be prime. Okay, so, I don't know why that popped into my head, but you got to understand, you got to think kind of loose to do mathematics well. Not that I'm claiming to do it well, okay, so we solve this equation. How? By converting it to a logarithmic equation. We use the inverse function. The inverse of 9 to the power is the log base 9. Just like this is log base 2. If you take a table of 9 to the x and switch the columns, you get log base 9. You take that for any base, you can do it. So the inverse of this is log base 9 of 437. Well, the inverse of the 9 to the power is the log base 9 function. If you identify your a and b, your a and c in the form of the logarithmic equation, you can see that this inverts in the way just very similar to this one, to 2x plus 4 equals log base 9, 437. And you can solve that, subtract 4 from both sides, and then divide both sides by 2, and right there's your solution. nothing to it. So you have this, but you got to do log base 9 of 437. Now I actually estimated that. You know, 9 to the second power is 81, 9 to the third power 729. That's roughly halfway between, but the logarithmic function humps up like this, so the log is going to be a little more than halfway between 2 and 3. So I went with 2.7. Now I don't know why I said we have approximately 2.7 here, except I was busy explaining something. I'm saying that the log of 437 is about 2.7. And the log of 9, the log log of 9 is about, well, I'm just going to say 0.9. That's not real accurate. Minus 4 over 2. And this is then going to be 3 minus 4 over 2, which is negative 1/2. So I didn't complete the solution. I stopped when I'd estimated this log, because I got to talking about that, and didn't finish the problem. Okay, well, here it's finished. If you put negative 1/2 in here, you get something that doesn't work at all. And that's because the log of 9 is not 0.9. Okay, sorry. Log of 9 is like really hard to estimate. So I'm going to put a question mark there. I don't have a good way to estimate the log log of 9. I could do the natural log, and I could get into that, but you take your calculator and figure this out. All this is wrong. This is a question mark here, and I'm unable to do a good estimate of the log log of 9. Now wait a minute. Take it back. Log of 10 is 1, so log of 9 should be close to 1. So I'm going to go back to 0.9. But we don't get a good result there. And we end up with 9 to the third power equals 437, and 9 to the third is 729. So this has to be estimated more closely, and so does this. Again, these estimates are very sensitive to small errors, which is no excuse. It's just a fact. Okay, it's hard to make those estimates. This one wasn't bad. I think this one's probably pretty good. This one's tougher. So we don't want to do that. Okay. So you plug this into your calculator, you get a number. You put that number up here and evaluate the exponent, raise 9 to that exponent. You should get this. Okay. Generalizing, y equals b to the x is equivalent to log base b of y equals x. If b was 2, then this would say exactly what you're used to seeing. So c equals b to the a is equivalent to a equals log base b of c. And you can use this for any b. So you can use it for 9, as we did here without really stating this. You can use it for just about anything else. Okay. A couple more laws of logarithms in an application. Rules for logarithms. First of all, log base b of c equals a is equivalent to b to the a equals c. That's what we've been using. Then you have log base b of a plus log base b of c equals a log base b of a times c. And this is because of the rule for exponents. It says b to the a times b to the c equals b to the a plus c. You notice you have a multiplication here and an addition here. Just like here, you have multiplication in here that becomes an addition over here when you expand it. Now the exact nature of the equivalence here, you don't want me to talk about that right now. Just here's the rule, and here's the reason for the rule. And what you need to focus on is that the log base b of a times c is log base b of a plus the log base b of c. You want to use something like a distributive law when you see this, and you want to say log of a times the log of c. And it doesn't work that way. Because of this, it works this way. The multiplication inside here becomes an addition here. Similarly, or analogously or something, if you multiply c times log base b of a, turns out that's a log base b of a raised to the c power. You can't just distribute the c through here and say c times a, because of course that would give you this, which is equal to this. Okay, so this can't be equal to this because this is equal to this, and this isn't equal to this. You might need to replay that 3 or 4 times to understand what I just said. It's not that important. Okay, there's the rule, and it comes from the power of a power law of exponents. The rule for the power of a power is b to the a raised to the c is b raised to the ac. Okay. Now another one that's really just a consequence of these two, and you don't really need it, but it's okay to have it, and you know it's kind of convenient. Log base b of a minus log base b of c, you take the log base b of a divided by c. You get choked up talking about logarithms. Okay, and that's because, it really is because b to the a divided by b to the c is b to the a minus c. That division gives you a subtraction over here, and this division gives you a subtraction here going the other way. Okay, that helps you remember them. Of course, you got to be real familiar with these laws. If that helps you remember these, it's good. Okay, so let's just take an example of an equation. 2 log base 5 of x plus log base 5 of x minus 1 equals 9. Okay? Well, 2 log base 5 of x is log base 5 of x squared. And that's added to the log base 5 of x minus 1. Well, now we have, and that's by application of this rule. Now we have a sum of 2 log base 5 expressions, and the sum is then going to be log base 5 of the product of those expressions. So that we're going to have log base 5 of x squared times x minus 1, and that's got to equal 9. Okay, well, I know I had to choose 9 because I can't do 5 to the 9th in my head. It's a couple million, I think. If we convert this to exponential form, we have x squared times x minus 1 equals 5 raised to the 9th power. But we can multiply this out, and we can subtract the 5 to the 9th from both sides, and we get this polynomial equation. Now, it's a cubic equation, it's not quadratic, and you're going to have a hard time even guessing what the roots might be. But if you use some of the techniques for finding roots of polynomials, you could solve this equation approximately. Most likely, though, you would just go to a computer and plug it in, the computer would tell you. Okay, just a short example of how these laws combined with this law, which of course is up here, can give you, or can be useful in solving an equation of this nature.